So this is a paper we had in EMNLP last year in November, so it's still quite recent, and it's about a very standard problem which is now becoming a little bit obsolete or solved, let's say, in natural language processing, which is summarization, although it's not yet solved in the setting that I will present here. So first of all, we'll start with some background, which I think might be useful for you since you might not be familiar with some core concepts in language models and NLP that might be useful. Then show our contribution to the experiments and finish with some final remarks. So for background, the task that we aim to solve. So cross-lingual summarization is the task of producing a summary of a document in a language that is different from the language of the original document. So in a way, it's the it combines summarization and machine translation in a single task. So in the example you can see here, you have a news article, in this case in English, and then a summary that was produced for this news article in Spanish. In multi-target cross-lingual summarization, instead of being interested in summarizing the document into a single target language, we want to obtain summaries in multiple languages. In this case here, you have the same document in English and then a summary in Spanish and a summary in Portuguese. Of course, this task, as is right now, you can just create a summary independently for each of the target languages. So there is no increased difficulty in the task just by the fact of being multi-target, but we impose an additional constraint, which is the summaries in different languages must be consistent. So they must have the same information, which is important because you as a user and someone who is receiving the information want to have access to the same information regardless of the languages you speak. So it's important to have systems that can ensure that regardless of the language in which the content is consumed, the user will be provided with the same information. So this is what we would like to achieve. We would like to have a system that provides summaries in different languages, all conveying identical information. And yeah, I already provided some motivation for this. The main motivation is then to ensure consistent communication across languages, which can be crucial, can be important in the context of information, so of news articles or whatever. But for instance, if it's legal documents or technical documents, it can even be crucial. So to ensure that the information is consistent across languages. So first of all, some back to basics in summarization. How do we address summarization currently? Well, a few years before, the state of the art was to use encoder-decoder architectures. They are both both encoder-decoder and decoder-only are transformer-based. In the case of the encoder-decoder, we will have a neural network called the encoder that processes the input document, generates a set of embeddings, and then a decoder that generates the summary token by token autoregressively. Currently, the state of the art for summarization and for the vast majority of the tasks in natural language processing is to have decoder-only models, like a GPT model, which basically is identical to the encoder-decoder, except that it doesn't have the encoder. So now we provide an instruction, the prompt, then the document we want to summarize, and then the model generates the summary token by token autoregressively. And here the instruction would be, for instance, given this document in English, generate a summary in Spanish and a summary in Portuguese. So it's just a prompt that describes the task that we want to solve. And how does it work? So the output of the model of the decoder is just the probability of the next token given the previous tokens. So this is all the model gives us. But we don't want probabilities, we want actual text. So on top of these probabilities, we need to have some criteria to select the next token. And for instance, one very obvious thing that you can do is to select the token with the highest probability at each decoding step. This is called greedy decoding. Or since you have a probability distribution, you can say, okay, I have a probability distribution, so I can just generate tokens according to this distribution. So for instance, if the token, I don't know, Apple has a 60% probability, then in 60% of the cases, you would generate the token Apple. Of course, if you apply this kind of probabilistic sampling, the generated text is non-deterministic. If you apply a greedy decoding or another variant of it called beam search, the text is deterministic, so that for the same input, you always have the same output. And then you select the token, you feed it to the input of the decoder. It provides you, again, the probability of the next token given the previous tokens, and so on and so forth. You repeat this process until the model generates a special token called the end of sequence that says, okay, I just finished my generation. Of course, a very straightforward approach for multi-target cross-lingual summarization is summarize and translate. And in summarize and translate, what you do is first you generate a summary in one of your target languages. So here the document was in Portuguese and you wanted to have summaries in English and in Spanish. So first you would generate a summary in English, and then you would translate this summary using a machine translation model into each of the remaining target languages. So in this case, there were two. So we would have the summary in English, and then we would translate the summary to Spanish. And this way, of course, we ensure that the summaries have the same information apart from errors that might happen in the translation, which is clearly the example here. And let's see why. So for instance, here we have information about a male nurse. And the gender of the nurse was clear from the text in Portuguese. But as soon as we produce a summary in English, this information is lost because nurse in English is a word that is the same for male or female. And so we don't have any information about the gender of the nurse in the English summary. And so when we translate this summary to Spanish, the machine translation model has to guess the gender of the nurse, and here probably because there are more female nurses than male nurses, the model decided that the nurse would be a female and not a male. So when we have this summarize and translate approach, one of the things that we might have is the so-called translation drift, where because of these cascade of translations, there is information that is lost. And of course, if there are, since we have two generation steps, one for producing the summary and another one for translation, we have error accumulation from these two phases. And moreover, a more subtle issue is that the choice of the pivot language can bias the summary. And what is the pivot language here? So the pivot language is the first language in which you generate the summary. So in this case here, we decided to generate a summary in English, and then translate this summary in English to the remaining languages. So this English language is called, the English language in this case is the pivot, because it's the language that we choose for the first summary. And it can influence the content of the summary, because the summarization model will decide which content to include in the summary, also based on the language that you have chosen. So the model might have biases that make it select this or that information depending on the language that it's using, which might make sense in some contexts, but not make any sense in others. And in our case, we don't want this to happen because we want our summaries to have the same information and to be neutral regarding the languages. So this choice of pivot language of the pivot language can also bias the content of the summary. If you are into graphical models, then you can easily see that summarize and translate corresponds to this graphical model. Even if you have never heard of graphical models and you are not familiar with it, you can kind of understand the flow of information in this graph. First, you have the source document. You choose a pivot language. In this case, it was English. Given the source document and your chosen pivot language, you produce a summary in the pivot language. And then for the remaining target languages, so for each target language, use the pivot language and the chosen target language and produce a new summary in the target language. So this step here, this first step would correspond to the summarization of document XO into the pivot, summary in the pivot language YPy. And then the last step here will be a translation from summary YPy in language Pi to summary YT in language T. And so how can we do better than this? How can we improve upon this summarize and translate approach that has the issues that we have seen? So one possibility is to change this graphical model and add this edge that directly connects the original documents to the target summary. So this way, every summary in all of the target languages will also be conditioned on the source document, and so can get information from the source document directly without having to pass through the pivot summary. And how can we do that? Well, we'll see that in a moment. But so now the first thing that we want to highlight is this property that both summaries are connected directly to the source document via these directed edges from the document to the summaries. And then we have also this undirected edge that connects the two summaries, and that corresponds to this term here in this equation, which basically determines how the summaries are generated. And this factor here, this phi of YT and YPy, is just a function that receives two summaries in different languages and measures how similar they are semantically. And you'll see how we can implement this in practice. But if you know what embeddings are, what sentence embeddings are, if you have cross-lingual sentence embeddings, you can just use the similarity of those embeddings. So a cross-lingual embedding is just a vector that encodes the semantics of a sentence, regardless of the language in which it was produced. So basically, two sentences that are the translation of each other should be mapped ideally into the same vector, and therefore have maximal similarity according to this function phi. So what can then be an algorithm to implement this graphical model? Well, we can first generate a summary YPy in the pivot language. Then we can sample k candidate summaries for each of the target languages. And then for each target language, use this function phi to choose the summary most similar to the pivot language. And by having this, we are ensuring that all the summaries in all the target languages are similar to the summary in the pivot language, and so they are similar to each other. And we ensure that, or at least we promote that they convey the same information because they are all similar to each other. However, this approach still relies in the choice of a pivot language. So this bias that may be introduced by choosing a language for the pivot summary is still there. And we want to do better than that. So we can extend this graphical model into something even more complex, which is this graphical model here on the right-hand side, where you have n target languages, and all of them are directly connected to the original document XO, but also connected to all the summaries in all the target languages are connected via undirected edges to all the remaining summaries in all the target languages. And what we mean with this, of course, it corresponds to a factorization of a probability distribution. So this graph is not just something that we have drawn just because we find it pretty. No, it has each of these edges has a very precise definition, but the intuition for it is that we want all of the summaries to be generated from the same source documents, and then these edges impose that they are all similar to each other. So they are all connected to each other, which means that we want to promote similarity between each pair of summaries here. So we want this set of summaries to be a set of summaries that are very similar and that ideally have the same information, the same semantics. And this is this factorization here. Again, if you are into graphical models, this will be easy. Otherwise, you can just forget about this. The only important part here is that this function phi of s, where s is the set of summaries. So it will be YT1, YT2, all the way up to YTN. This function phi s is the sum of all pairwise similarities between all summaries here. So between YT1 and YT2, YT1 and YT3, YT2 and YT3, and so all possible pairs that you have here will correspond to a term here in this sum of similarities. So you can see here that this grows quite fast. So you have n combinations of two pairs here of summaries, where n is the number of target languages. And so now if we want to extend our previous algorithm for this case, now what we would do would be to generate k candidate summaries for each target language. And here, when we say generate k candidate summaries for each target language, is by using sampling. So if we use sampling in a language model, we can get for the same document multiple different summaries. For instance, if you ask ChatGPT to provide you a summary for a news document, k consecutive times, ChatGPT will provide you k slightly different summaries, and you can control how different they are by controlling the temperature of the sampling. But the idea is that it's not deterministic, so you can have diversity in the summaries, and you use this here to obtain k different summaries in each of the languages for the same document. And then we would like to choose one summary for each target language so that the sum of the pairwise similarities between every pair of summaries is maximum. The problem is that this choice is a combinatorial problem that is basically intractable. So it grows exponentially with the number of candidates summaries that you have. So basically, it grows exponentially with k. So this problem is intractable. By the way, it was exponential with the number of languages, not with k. It's k to the power of n, the number of combinations that you have, if I'm not wrong. But there is a change here that we can do, which makes this maximization problem tractable. So instead of considering all the pairwise similarities between the summaries in all the languages, if we assume that the languages have an order, then the problem becomes tractable, and you can find the exact maximum using the shortest path in a graph using basically Dijkstra's algorithm. And I will explain you how in a minute. So for instance, suppose that you want to produce a summary in 4 different languages, in this example, English, Portuguese, Dutch, and Spanish. The order of the languages is completely arbitrary, so you just define some random permutation of the languages. In this case, English is the first, then Portuguese, then Dutch, then Spanish, and so on and so forth. And then you can build this graph where you have a dummy source node and a dummy sink node. And then you have these layers where each layer corresponds to a language, and each node in a language corresponds to a summary. So basically, here we have 4 summaries for each of the languages, 4 candidate summaries for each of the languages. And then these edges here correspond to the similarity between, for instance, this edge here corresponds to the similarity between this second summary and in English and the first summary in Portuguese. So we can measure the similarity by using this cross-lingual embeddings model, and then the similarity of those vectors, for instance, Euclidean distance or cosine similarity, or your favorite metric of similarity. So basically what you have is a directed weighted graph from source to sink, and all you need to find is the shortest path, or in this case, the longest path from source to sink, where the length of each path is the weight that is assigned to the edge, which corresponds to similarity. So you want to find the path from source to sink such that the sum of these similarities in the edges is maximum. And you can use Dijkstra's algorithm for that and find it in roughly quadratic time instead of exponential time. So you have gained a lot. Of course, this is based on the choice of on the permutation of languages, but you can somehow assume that if the summary in English is similar to the summary in Portuguese, and the summary in Portuguese is similar to the summary in Dutch, then with some degree of confidence, you can also assume that the summary in Dutch is similar to the summary in English. So you can assume this transitivity property in the similarity, and then use it to find the best set of summaries efficiently. So what we do is basically exactly this, but instead of considering just one permutation of the languages, we consider m different permutations. We find the best path for each of the permutations, and then we have m of those permutations, and with each of those m, we can evaluate the similarity exhaustively in each of them by considering all the pairwise similarities, and then just choose the best among those m candidates. So we have improved a lot in terms of computational time. So in terms of the methodology, that's basically it. Now let's see how we implemented this in practice. So for the many-to-many cross-lingual summarization, we used an MT5 model. In this case, it was an MT5 model that was fine-tuned in a cross-lingual summarization dataset. So we also experimented with just prompting an LLM, but our best performing solution was with this model that was fine-tuned on a cross-lingual summarization dataset. And then to evaluate the similarity between summaries in different languages, we used basically the cosine similarity of Sonar embeddings. Sonar is an embedding model that, as I mentioned earlier, you give it a sentence in a language and it produces an embedding for this sentence that basically ignores the language ideally and only cares about the semantics of the sentence. And so we have all that we need to implement the model. Here, there were other metrics that we could have used to implement this similarity. So if you look for quality estimation metrics in machine translation, basically any of those would work here. We use this one just because it was the most recent model at the time, and I think that it still is. So for in our experiments, we used clusters of this cross-sum dataset, which contain documents and summaries in up to 7 languages. So each document will be summarized in up to 7 languages. And so we used each language in the clusters as the source language, and then we generated summaries for all the languages in the cluster. And so we evaluated, of course, regarding the evaluation metrics, we used usual n-gram overlap metrics that basically compare, let's say, word by word, the summary you produced with the gold summary, with the target summary of the data set. And these metrics, you might have heard of Rouge metric, which is the standard for that. But apart from evaluating the semantics, the similarity of the summaries to the targets, we also want to evaluate if our summaries, if our set of summaries is actually consistent. So if the summaries that we produced actually have the same information for different languages. And so for these, we use these Comet, Kiwi, and Blazor, which are basically quality estimation metrics for machine translation. What does it mean? It means that you can give it 2 sentences, like it's like Sonar. So you give it 2 sentences and it gives you a score of how similar those sentences are, sentences in different languages, of course. So, and these are the results. So this M2MS is basically a model that's a many-to-many summarization model that generates summaries for each of the target languages independently, so without caring about the semantic coherence of the produced set of summaries. And we can see here that, unsurprisingly, it achieves the best similarity to the target summaries. But when you look at the coherence of the produced set of summaries, it's the lowest, basically, because it's basically generating a summary for each of the language independently. So it doesn't care about the information that is in different summaries. Then you have this S&T, which stands for summarize and translate. So here, what we do is first, we generate a summary for the document in the language of the document. And then, so if the document is in Portuguese, we first generate a summary in Portuguese. And then we translate this summary into all of the remaining target languages. And again, unsurprisingly, we see that it achieved the best semantic coherence because different summaries are direct translations of each other. So they are basically, apart from minimal translation issues, they are basically the same. But when you evaluate the similarity to the targets, it's basically the worst because the translation just degrades it too much. Then we have Mistral. Mistral is a large language model, so it's a model that doesn't need to be trained, ideally. So this was achieved only with prompting. The model was prompted to produce a summary for each of the languages with a constraint that the summaries must have the same information. And surprisingly, it actually does this job of producing summaries with the same information quite well. But then the similarity to the target, the gold summaries, is very low, is the worst. And finally, our two approaches, this pivot re-ranking is the approach, our re-ranking approach using a pivot language, and this neutral re-ranking is the last approach that I've shown, which uses this Dijkstra's algorithm and treats all target languages equally without relying on a pivot language. And you see here that it achieves the similarities to the target summary are almost as good as many-to-many summarization, and it significantly improves the semantic consistency of the produced set of summaries compared to this many-to-many summarization. So it really gives a boost in quality regarding that. So when we can see here, so in this case, we used 8 candidate summaries for each of the target languages in the table that I've shown you before, but it's also interesting to see how the metrics evolve if we increase the number of candidate summaries for each of the languages. Of course, it comes with some computational costs, so the time that it takes to produce the set of summaries clearly increases, of course, but we can see that we can keep the semantic, the similarity to the target summaries fairly constant as we increase K, and the similarity of the set of summaries, so the semantic consistency of the set of summaries improves monotonically as we increase K, and this improvement is more noticeable in our neutral re-ranking approach than in the one that relies in the pivot summary. So these two metrics are evaluating this, and you can see that especially regarding this comment QE, it really gains if you improve K. If you increase K, you really get improvements on the semantic similarity of your set of summaries, which actually shows that the model is doing what it's supposed to do. So finally, we introduced this noble task of multi-target cross-lingual summarization. No one had addressed cross-lingual summarization in this multi-target setting before. And we proposed a language-neutral approach for that, which is based on a re-ranking or best of N, best of K in this case, to follow the notation that we used approach. And we have shown that this the approach that we followed successfully improves the semantic coherence of the produced set of summaries, and we see it as being this task as being important in legal, for instance, for the summarization of news documents, of course, but much more important in technical or legal domains, where having precise and consistent information might even be crucial. So if you're interested to know more or to look at the code or reproduce experiments, we have everything publicly available. And of course, the paper was published at EMNLP, so it's also publicly available. So I don't know if you have any questions or comments. I'll be very much looking forward to hear them.